So let's start this next section, basic properties of the Riemann integral. So in this section we are going to see properties similar to the ones we have already seen for piecewise constant functions. And in fact, this theorem is going to just be like the one we have seen for piecewise constant functions, and will subsume that theorem for piecewise constant functions, because this theorem is also going to talk about piecewise constant functions, but in general it will talk about bounded Riemann integrable functions, and piecewise constant functions form a subclass of the class of all bounded Riemann integrable functions. So let's see what we already know what the properties are, so let's just see the statement. It starts off exactly similarly like that one started. We have a bounded interval on which we have two functions defined. But this time, instead of piecewise constant functions, we will have Riemann integrable bounded functions. Let I be a bounded interval and let f from I to R and g from I to R be Riemann integrable functions on I. When we say Riemann integrable functions on I, we need not again say that they are bounded, because Riemann integrability is defined only for bounded functions. Then the following are true. And part A has the sum of f and g, which will also be Riemann integrable. The function f plus g is Riemann integrable on I, and its integral over I is nothing but the sum of the integrals of f and g over I. Okay, just exactly like the similar result for piecewise constant functions. Next, B. For any real number C, the function, the multiple of f by C, that is Cf, is also Riemann integrable. Multiplying a Riemann integrable function by a real number again gives us a Riemann integrable function. The function Cf is also Riemann integrable, and the integral of Cf over I is equal to C times the integral of f over I. Combining these two rules, we have next the difference of f and g. The function f minus g is Riemann integrable on I, and its integral is the corresponding difference of the integrals of f and g. Before I clean this part, let us just think of how this is following from parts A and B. Although you may know, but let's just see once again how it follows from parts A and B. See, first of all, actually there are two parts of this conclusion. The first part is that f minus g is Riemann integrable, and then the second part tells us what the integral of f minus g is. Now, how do we get the first part? You see, g is Riemann integrable, that's given. So you can multiply g by the constant minus 1 to get minus g. So by part B, minus g is also Riemann integrable. And so the sum of f and minus g will also be Riemann integrable by part A. So that's how we are getting this conclusion that f minus g is Riemann integrable. But that's not all. We also get the formula for its integral. Which is nothing but this. F minus g is equal to the integral of f minus the integral of g. And this also comes from these two formulas. Because f minus g is f plus minus g. So by part A, that is integral of f plus integral of minus g, and then minus g is minus 1 times g, so you can take minus 1 outside by part B, and that's how you get this. Next, non-negativity, part D. If the function f is non-negative, that is all its values are non-negative real numbers, for all x in I, then the integral of f over I is also a non-negative real number. And in this case, this is you already know this from your school course, that is from calculus, that in this case, this quantity is the area under the curve. Under the curve means under the graph of this function, and between the boundaries of the interval I is a bounded interval, so I is going to have a left end and a right end. Between those two vertical lines below the graph of this function and above the x-axis, you have a region, so this is the area of that region. Now part E again comes from two previous parts like this. If f of x is greater than or equal to g of x for all x in I, then the integral of f is also greater than or equal to the integral of g. So for this you have to apply parts C and D. So what you do, you consider this condition. So this condition, let me just show you how this comes. This condition gives us what? It is equivalent to this, right, for all x in I. But what is this? This is nothing but the f minus g image of x. This means that the function f minus g is non-negative. Also, by part C, f minus g is Riemann integrable on I. And so you can apply part D to f minus g. Part D will give you this conclusion. Greater than or equal to 0. And then again you apply part C, this equation. So this integral becomes what? Integral of f minus integral of g. So that becomes non-negative. Now add integral of g on both sides, and that way you get this. As this comes out as a consequence of parts C and D. But, well, not every part is going to come out as a consequence of something else so easily. Some of them we have to prove from scratch. We will see when we go to the exercises, because the proof of this result is one exercise, the first one of this section. After E, we have F. F is really easy, and it in fact is a special case of even piecewise constant functions. That is, if we have a constant function, if f say is a constant function, then what will be the integral? If C, let me write it like this, if C is a real number such that f of x is constantly C for all x in I, then the integral of f over I is C times the length of I. We have already come across this same result, I should not say same result, but an exactly similar result where f was a piecewise constant function. Well, I mean, here also f is a piecewise constant function, but what I am trying to say is that we have already seen this result before when we developed integrals for piecewise constant functions. So the same thing happens here also. Next, G. In G, we can extend f to a larger function. If J is a, or okay, no, let me not start with if. Let me start like this. Let J be a bounded interval just like I, but J is a larger interval in the sense that J will contain the interval I within it as a subinterval. And on J we are now going to define a function, a part of which will be our f. Be a bounded interval such that I is a subset of J. Define a function capital F on J, real valued of course, by the following rule. F of x is the same as small f of x if our input belongs to I, but is defined to be equal to 0 if the input belongs to j but does not belong to I. It's in the difference j difference I. Then this is a legitimate well-defined function. It's kind of, you can call capital F an extension of small f. But the restriction of capital F to I is nothing but small f. Then, just like small f, capital F is also Riemann integrable on its own domain, that is on J. And its Riemann integral over J is the same as the Riemann integral of small f over I. And the integral of capital F over J is the same as the integral of small f over I. And then there is one more. This time we are not going to extend f small f, but rather we are going to break up the interval I itself into two subintervals. Essentially, we are going to consider a partition of this I where there will be two subintervals. Let j comma k be a partition of I. That means these subintervals are going to, or these symbols are going to denote subintervals of I. All the conditions that you need for such a collection to be a partition is there. Okay. They themselves have to be bounded intervals, all those things. That each point of I belongs to exactly one of them. So this is a partition having two elements, a partition of I. Then the restrictions these two restrictions, the restriction of f on j, this is going to be a real valued function with domain j, and again the restriction of f but to k. This is a function from k to r. These two restrictions, as if we have broken up the function f itself into two parts, depending on these two parts of the original domain I. These restrictions are also Riemann integrable, just like the original function f are Riemann integrable on their respective domains, that is j and k. On j and k respectively. Also, the integral of f over I is equal to the integral of the first restriction over j plus the integral of the second restriction over K. Okay, so these are the various parts of this result. Now its proof is the first exercise of this section. So you know how we deal with the exercises. We are going to make a community post where we will see the solution. Alright. Now after this there is a remark which simplifies this notation slightly. Whenever we are dealing with an integral of a restriction of some function, we do not normally write the full notation of the restriction. That is, in place of integral of f bar j over j, we simply write integral of f over j. We write this in place of this, which is actually the more accurate notation. But when you are restricting the domain from I to j, it is to be understood that we are actually considering the restriction of the given function f to that smaller subinterval. And there is no possibility of any confusion. And the notation is also made slightly simpler, so that's why we are going to follow this. Now, besides these algebraic combinations of Riemann integrable functions, we can also consider something else. In other words, besides sum, difference, multiplying a Riemann integrable function by a scalar and these things, there are other ways of producing Riemann integrable functions from f and g. So the next result gives us two such ways. So this is Theorem 11.4.3. It has a name also, like minimum and maximum preserves Riemann integrability. I am not going to write that. Instead, let's just see the result. Again, just like that one, let I be a bounded interval and let f from I to R and g from I to R be Riemann integrable functions. On I, then these functions max of f and g from I to R and mean of f and g are also Riemann integrable. On I, where although we have already encountered these functions, but the author has again given the definitions. Let me write it over there. The definition of max of f and g is nothing but the maximum of the f value and g value. Similarly, this is the minimum at every input x coming from our interval I. Okay, now its proof is not an exercise. Its proof is there in the text, in the body of the text itself. We are, however, not going to see the proof today. We will see it in the next video. Because I have noticed that, unfortunately, making long videos is almost pointless. That is why I have shortened the video length, so that you also don't get bored and take things in smaller, more palatable chunks. So with that, I just end tonight's video here itself, and tomorrow also we have one upload that will be on we are going to again go back to trigonometry from class 11. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.